we're now going to explore the concept of orthogonality in the context of vector subspaces being represented as the spanning set of some collection of other vectors, right? First, let's recall what it means for, let's just look at the context of two vectors, right? So kind of like a Calc 3 review here. So here's kind of a recall. Two vectors, let's say U and V in Rn are orthogonal. Let's say if and only if their dot product is 0, right? And why is this the case? Well, orthogonal really, if you'd like to think about it this way, you could just think about it as perpendicular, etc., blah, 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 perpendicular, right? Remember, we had the property that U dot V was magnitude of U, magnitude of V, cosine theta. Well, if that's 0, this dot product is 0, then that necessarily implied that theta was pi over 2, right? Where here theta is the interior angle between the two vectors, U and V. And so, you know, here's kind of a recollection of what it means for two vectors to be orthogonal, right? We don't necessarily have to have that it's just two vectors. We had another example here is when we had n, let's let this be a normal vector to a plane in R, let's just say R3, for example. It could be Rn, let's say Rn. Right, most of the explicit, like when we were finding formulas for these, or equations for these planes, it was in n equals 3, but, you know, in for arbitrary n here, we have some plane, and then we have a normal vector n, right? Well, this plane is described by n dot pq is 0. Well, we have that this is true for every vector pq describing this plane. And so here's an example of when a vector is orthogonal to a subspace, right? And so we're going to explore this concept more in depth. So what do we have here? We have that, well, let's give a definition here, just to be precise, right? So here we've talked about when two vectors are orthogonal. Here we've talked about when one vector is orthogonal to a family of vectors, right? And we'll be more interested in this case, not necessarily in the case that these vectors make up a plane, but that they span some subspace. So let's consider the set of vectors. Let's call them U1, U2, up through U. Let's use M. We usually use N for like the dimension of our ambient space, right? Let's say N here. We say this set is orthogonal if for every I and j where I and j run from 1 to m, right? So it's just indexing like two different vectors, right? Basically what I'm saying is take every possible pair of vectors in this where I is different from j. Then we say that this set is orthogonal if for every pair we have that ui dot uj is 0, right? And so this is what it means for a collection of vectors to be orthogonal. And this is what we're going to be interested in because we're interested in looking at a collection of vectors that will describe, the span of a subspace or a basis, or whether they're linearly independent or not, right? We care about this context right now, these collections of vectors. Okay. We have kind of a more restrictive concept as well, and that's called being when a set of vectors is orthonormal. So let's give another definition here. So an orthogonal set, let's say, call them W this time, W1 through Wn is orthonormal if we have the following property, that Wi dot Wj is equal to the Kronecker delta symbol. And if you haven't seen the Kronecker delta symbol, what it means here, that's not a very good delta, sorry. Right? The Kronecker delta symbol is 1 when I equals j, and it's 0 when I is different from j. And so if we also, right, not only is this collection W1 through Wn orthogonal, we also have this property that when you take the dot product of any of these vectors with itself, you get 1, right? What does this mean, right? What does this mean? Oh, by the way, this is Kronecker delta symbol. Okay, so how do we interpret this a little more intuitively, right? Well, basically what we're saying is that Wi dot Wi is equal to 1. So when do we get that, right? What kind of vectors would we have in an orthonormal set? Well, recall that Wi dot Wj, or let's not use, because this is in general, right? Let's recall that U dot U is equal to the magnitude of U squared. So what does that mean in this context for an orthonormal set? Well, we have Wi dot Wi is equal to the magnitude of Wi squared, which equals 1, which implies that the magnitude of Wi equals 1. So an orthonormal set is an orthogonal set where every vector has magnitude equal to 1, right? So what's an example of an orthogonal set, or an orthonormal set, or a set that's neither, right? So let's look at some important examples here. Let's find one that's not orthogonal, right? Well, really, you can come up with a lot of these. All you have to do is come up with a collection of vectors such that at least one pair gives you a non-zero dot product. Well, let's just do an example with 2 vectors so we get the idea. Let's consider the set of vectors 2, 3, 1, 1, right? This is an example of a set of vectors that's not orthogonal because, well, when you take the dot product, 2, 3, dot 1, 1, you get 2 plus 3, which is 5, which is hopefully not 0, right? So there are a lot of examples of collections of vectors that are not orthogonal. What about something that's orthogonal, but not orthonormal? Well, you would need a collection of vectors where every vector is perpendicular to every other vector, right? Meaning the dot product of every pair is 0, but at least one of these vectors needs to have magnitude other than 1, right? So let's look at this example. Let's have the first vector be 1, 1, the second vector be negative 1, 1. Well, to show that this is orthogonal, we can show that 1, 1 dot negative 1, 1 is negative 1 plus 1, which is 0. That gives orthogonality. But if you take the magnitude of 1, 1, you get square root 1 squared plus 1 squared, which is root 2, which is not 1, right? So this is an example of a set of vectors that's orthogonal, but not orthonormal. Let's find an example that's orthonormal. An example that's orthonormal would be, let's see, what did I use? 1 over root 2, 1 over root 2 for the first vector, and then negative 1 over root 2, 1 over root 2. So let's consider this set here. When we consider this set, we can see that the dot product is 0 in the same way. So first vector dot the second vector, and that's a negative, by the way. When we take this dot product, we're going to get negative 1 over root 2 plus 1 over root 2, which is 0, which means that it's orthogonal. Well, and then we would have to calculate magnitudes, right? So what's the magnitude of 1 over root 2, 1 over root 2, and then negative 1, well, what am I doing? Right, let's calculate magnitude one at a time here. So this would be square root 1 over root 2, quantity squared, plus 1 over root 2, quantity squared, which is square root 1/2 plus 1/2, which is 1. Same for the other vector, which implies orthonormal. Okay, and what you may have noticed, which is great if you did, and it's fine if you didn't, is I used the orthogonal set to find or construct an orthonormal set. Well, how did I do this? How are these related? You'll notice what I've done here is I've taken, in the orthogonal set, I took the first vector and I scaled it by 1 over root 2. And I also scaled the second vector by 1 over root 2. And I got exactly this. And why did that make it orthonormal? Well, remember, if you have a vector v with magnitude not equal to 1, then, or even if it is equal to 1, so if you have a vector v, then u, which is defined to be v over its magnitude, or scaled by 1 over its magnitude, is a vector of unit length in the direction of v, right? We know that already. So what you can do, if you already have an orthogonal set, you can always construct an orthonormal set by scaling every vector by 1 over its magnitude. So here's kind of, let's see how I listed it. Just as kind of a conclusion or an observation. If V1 through Vn is orthogonal, then you can always find an orthonormal set U1 through UN, where UI is equal to VI, whoops, divided by the magnitude of VI, right? And so you can always do this. And why do we care, right? Why do we care about doing that? Well, when we construct an orthonormal set from an orthogonal set, we have that UI points in the same direction as VI for all I, right? Because this is precisely a vector of unit length in the direction of V. And so what this means then is this is an orthonormal set such that the span of V1 through Vn is equal to the span of U1 through UN. And we'll see later why this is important, right? If you'd like a small example, you could span R3 by, let's say, the vectors 5, 0, 0, 0, 2, 0, and 0, 0, 420, right? This would be a linearly independent spanning set for R3, but it's not very convenient, right? Because units then, how you would measure like length or angles or whatever, it would all be dependent upon multiples of these numbers. And that's not convenient at all. But what we could do is we could pass from an orthogonal set to an orthonormal set. And if we did that in this particular example, we would construct the standard unit basis for R3, right? I hat, J hat, K hat. And so you can see this is a much more convenient coordinate system or description of R3, right? So, okay, I think that's where I want to stop for now. The next video is going to be, we've been looking at what it means for vectors to be orthogonal and orthonormal. But what does it mean for a matrix to be orthogonal or orthonormal? So that's what we'll explore in the next video.